So last class we started looking at the voltage mode passive mixers, and we'll quickly review what we did last class. So the first mixer we considered was a return to zero mixer, which is basically just a switch under resistance. And when the switch is on, the output voltage follows the input voltage. When the switch is off, the output voltage returns to zero. And we quickly looked at the fundamental component. It seemed to have a gain of 1 over pi from RF to IF port. And if you have a single balance mixer, you can have twice this gain. And also if you have just a single mixer without the single balance version, the actual DC value is 0.5. So you have to be careful because the RF voltage also appears at the IF port with a gain of 0.5. And therefore if you have any even order nonlinearity at the RF port, that will cause a term which will fall on top of your baseband at the IF port. Then the next circuit we considered was the sampling mixer, and in this case you just have a switch and a capacitor. So in this case, instead of returning to zero, the voltage across the capacitor at the end of the LO half cycle is held on the capacitor till the beginning of the next half cycle when the switch turns on. So therefore you get a waveform which looks something like this. And now this we decomposed into two portions. The first portion was the same as the return to zero waveform, and we know what the gain is. The second portion is a sample and hold kind of system where it holds the value, it samples the value at the end, at the negative edge of the LO waveform, and holds that till the next time when the switch turns on. In which case this portion will go to zero, the other portion will actually do the tracking. Right? So we just decompose that same y of t into y1 of t and y2 of t. And we derived expressions for each of these based on the fact that they are reminiscent of a square wave which is just a pulse convolved with a pulse train, with an impulse train. So we express each of these, both y1 and y2 in the next half, in terms of the input and some form of multiplication or convolution with the pulse and the impulse train. And any delays are also accounted for. Using these and some basic Fourier transform identities, we came up with a specific expression for y1 of f at the IF port for each of these. So we got y1 of f and y2 of f, and y1 of f is just the x of f minus f naught and x of f plus f naught. Translate, in other words, it is the input frequency translated by the LO frequency with a gain of 1 over pi and a phase shift of 90 degrees. y2 of t has a Fourier transform y2 of f, and for this specific condition, in other words, for a received mixer, when the IF or the baseband is much smaller than the LO, we said that we can make a certain approximation and reduce the expression for y2 of f at the IF frequency to something which looks like this. In other words, the input signal is being translated in frequency from f to f minus FLO, and the gain of this is 2, and there is no phase shift, and therefore the overall output or the magnitude of the overall output has a conversion gain which is root of 1 over pi square plus 1 over 4. And this conversion gain is 0.593. if you have a if you have a single balanced version of this particular mixer, it will have a gain which will be twice this, which happens to be 1.186, and surprisingly, or at least somewhat surprisingly, the gain is larger than 0 dB. But we know this was possible because the fundamental of a square wave is larger than the amplitude of the square wave itself. There is a 2 by pi factor. And in the next portion, what we said is, if we move to a double balanced mixer, okay, what you will find is that the conversion gain will end up being 2 by pi, whether you consider a return to zero mixer or a sampling mixer. The reason for that is, unlike a single balanced mixer, the outputs are asserted at all times and have a certain relationship with the input. They are not left floating at any time. Okay, so because of that, if you actually figure out the conversion gain of this, it ends up being 2 by pi, irrespective of whether you have a resistor or a capacitor load. And finally, we also looked at current mode passive mixers, where the input is an RF current instead of an RF voltage, and the output now needs to be sent through some kind of baseband impedance to be converted to an IF or a baseband voltage. And I also mentioned that the behavior of this particular mixer, of the current mode mixer, is different from that of the voltage mode mixer, and something as basic as the input impedance is different, because the mixer is a time variant circuit, and therefore the impedance changes depending on whether it's driven with a voltage or driven with a current. And we will try to derive the expression for both of these input impedances in today's class. So the first case we'll take is the case of the voltage driven passive mixer. So as before, our input was x of t, our output was y of t, and let's say the switch is L1 and is driven with some 50% duty cycle LO waveform. So it takes an input current In of t, and let us say the output current is I out of t. What is the relationship between the input current and the output current? So this is In and this is I out. What should the relationship be between In and I out? They have to be equal. Okay. In of t should be equal to I out of t. So that's the first thing we'll state. And remember that we decomposed y of t into y1 of t plus y2 of t. This we have done yesterday, and we do know the expressions for y1 of t and y2 of t. And we also know I out of t is nothing but CL dy by dt. Okay, that is just the current through the capacitor. I out of t is nothing but the current through the capacitor, which is CL dy by dt, where y of t is the output voltage. So your In of f j omega CL times y of f. Okay, this is your input current. Now we know that y of f has a huge number of frequency components, and therefore In of f will also have a huge number of frequency components. How do we define the input impedance? Normally, if you look at x of t, it is going to be a narrowband signal. So we also know x of t is narrowband. Okay, at some RF frequency, and therefore we are interested in the input impedance at this RF frequency, and therefore we are interested in the input current at this RF frequency. Yes, it's the same. I out of f is the same as In of f. Okay, because the switch input current has to be equal to the output current. So that is the first thing I put up here. Okay. Frequency component of In of f corresponding to this, right? How do we figure out what this is? So we are interested in the frequency component of In of f. That's easy. We know y of f, right? We know y of f. We have just determined that in yesterday's class. It has y1 of f and y2 of f. Each one of these has many components. What do we do to figure out the frequency component corresponding to the input? So let's take the example of y1 of f. So this is the overall expression for y1 of f, correct? To find out the output IF voltage, we set k equals to plus or minus 1, because that will give you f f plus or minus FLO, because that really shows you what the translated voltage is from the input to the output. So k equal to plus or minus 1 translates the RF frequency to the IF frequency by subtracting or adding FLO. If you are interested in finding out the input current at the frequency of interest at the input, you have to set k equal to 0. Okay, so that you will basically set this to delta of f and then do the corresponding evaluation of y of f, y1 of f and y2 of f at that frequency, at the input frequency. So let's write down the expressions for y1 of f. So it's x of f convolved with 1 by j omega into 1 minus e per TLO by 2 times the impulse train. This was y1 of f. y2 of f was x of f convolved with the impulse train e power minus j omega t LO by 2 delta of f minus FLO times 1 by j omega 1 minus e power minus j omega t LO by 2. So this is the expression for y1 of f and y2 of f. So we are going to set k equal to 0 for the frequency component of interest. Okay. So what does y1 of f decompose into? So this just becomes delta of f, right? What happens to the, this becomes just delta of f if you set k equal to 0. So what happens to this expression, this whole circled expression? Yeah, so what is that? Think of 0 as 1. Are you missing out a factor? There's a TLO by 2, right? And then, okay, so y1 of f will reduce to, in fact, there will be a half factor because TLO will also get cancelled when you actually, because you have j omega t e power minus omega TLO by 2, and then you have j omega TLO in the denominator, so it will end up as a half term. So the first term will give you a x of f by 2. Now the second term gives rise to 1 by TLO x of f 1 by j omega into 1 minus e power minus j omega TLO by 2. Okay, so obviously this is a frequency dependent input output voltage term. Okay, so now if we want to calculate Zn of f, we defined it as In of f over x of f, or rather Yn of f is nothing but In of f over x of f. So it's j omega CL into half plus 1 over j omega TLO into 1 minus e power 2. This is the expression for the input impedance. So now we'll need to find out in different regions or under different conditions what this actually reduces to, because you now have to figure out what the relative values of omega, so FLO and FR, right? F was the input frequency, FLO is the LO frequency. Now, depending on whether you have a transmit mixer or a receive mixer or something else, this value would change. So let us take the simplest example. Let us say omega was much smaller than 2 pi FLO. Zn of f ends up being what? Or Yn of f reduces to what? It just ends up being j omega CL, because the second term also becomes half, the first term also becomes half, so you get equal to j omega CL. So in other words, if the input frequency was much smaller than the LO frequency, the switching rate of the switch, the output capacitance just translates to the input directly. Okay, so you have a load capacitance CL, it looks like a load at the input. What case is this? Omega much smaller than 2 pi FLO? Huh? Sorry? Upconverting mixer. Okay, correct. So this would be like a TX upconverting mixer. So the next case is omega equal to, we just say omega equal to 2 pi FLO. This is the case of a direct conversion receiver. The first term stays half, the The second term becomes 1 over j pi, becomes approximately 1 over j pi. Zn of f yn of f, sorry, is j omega cl by 2 plus 2f cl. So in other words, so it looks like a capacitance of Cl by 2, half the capacitance, and a resistance of 1 over 2f Cl in parallel. Okay? The third case is when omega is much smaller than 2 pi SLO. The second term becomes negligible and your Zn of f is just, sorry, j omega Cl by 2. Okay? So this is the input impedance of this particular sampling mixer at different frequencies depending on what the input frequency is related to the LO frequency. If you want to convert this to a single balance mixer, okay, you will have to divide this by half. If your switch is non-ideal and has a switch resistance, you will have to add the switch resistance and then divide it by half. So for a single balance passive mixer, so it's half of switch resistance plus 1 by 2FCL plus, this is for a direct conversion receiver, right, when F is approximately equal to SLO. Correct. Correct. The capacitors look like a resistor of 2FCL, if I am not mistaken. The only question is whether the input capacitance is also taken into account. Yes. Correct. No, but that's okay. That is true. But if you just take a capacitor and see the switch, it does look like a resistor at these, which depends on the sampling frequency. Obviously, the complete expression for that also includes the capacitance also. Okay, it is not just a resistance but a capacitance also. Now, it is quite possible that in those cases, you use it at frequencies where the bandwidth of the circuit is much larger than the resistance you are trying. So, in other words, you sample it at a certain rate where the CL by 2 is, impedance of CL by 2 is negligible compared to this resistance. Okay, you will have to choose F in such a manner. But yes, this is exactly the same thing. Yes, you have a question? This C part. Sorry, this one. So if omega was much larger than TLO, right? This term becomes very small, right? E power minus j omega TLO by 2 becomes 0, tends to 0. So this is just 1 over j omega TLO. Omega TLO is very large because omega is much larger than omega LO. So you're just setting this whole term to 0. Okay? Yeah, it is. So this is for a voltage mode circuit. Now for a current mode passive mixer, so we already made a couple of observations, which was Zn could be different. Because the passive mixer is time variant, and we will again define Zn as the input voltage over the input current, or define Zn of F is Vn of F over In of F. Now we need to figure out what a current mode passive mixer will be driven by, what kind of impedance will be placed at on the other side, and then decide what the impedance, input impedance could be. So a hypothetical case. So I have shown a low noise transconductance amplifier whose output impedance is very large. Okay, so maybe you have a blocking capacitor to block out the DC, and then there is some baseband impedance connected at the output. Okay, so this generates a voltage, let's say V1 and V2, and the output is taken as a difference between V1 and V2. So this gets LO plus, this gets LO minus, and let us say this is delivering a current In and generates a voltage Vn at the input. So now we need to make some assumptions. So let us say this impedance ZBB has an impulse response h of t. Okay, let us say this has an impulse response h of t. What is V1 of t? V1 of t is the input current In of t multiplied with S of t, okay, and then that is convolved with h of t, which is the impulse response of the impedance, correct? And S of t is nothing but the single-ended LO voltage. So it goes from 0 to 1. It's a square wave from 0 to 1 with a period TLO. And 50% duty cycle. So now V1 of F is nothing but In of F convolved with S of F multiplied with the baseband impedance ZBB of F. And we also know that if the fundamental of S of F is at a certain frequency FLO, so you convolve In of F with that fundamental frequency to translate the input to the IF frequency. So convolved with first harmonic of S of f gives you the frequency translation you are interested in. Okay? Maybe it's some IIF of f. Then this V1 of f is IF of f multiplied with the baseband impedance. Okay, so you get first frequency translation by convolving with S of f, and then you multiply it by the baseband impedance to create the voltage. Now, the basic mixing action is to convert this input current, translate this input current into an output IF current. Okay, the minute you actually multiply this with the baseband impedance to create a voltage at the output node, that voltage again mixes with the switching waveform to create a different behavior. Okay, so in other words, if this was going into a low impedance node, we are not creating any voltage, the matter ends there. The minute you try to multiply it with an impedance, you are going to create a voltage there, which can again mix with the switching pair. Okay, so V1 of f or in the time domain, V1 of t and V2 of t with S of t. Okay. What happens when V1 of t and V2 of t are multiplied with S of t? They are mixed. So what was the baseband voltage V1 of t will get translated to an RF voltage VRF of t or V1 VRF of t. So are multiplied with S of t and upconverted to the desired RF frequency. So now what that means is that creates an additional component of the input voltage. So for example, use the next page. So let us say in the frequency domain, the input current IN of f looks something like this. So this is the current coming out of the LNA. What happens? You are convolving this with S of f, and the fundamental of S of f is that plus or minus FLO, and after convolution you get the baseband current. So this is S of f. After convolution you get your IF of f. You of course get other components also. Now this current is multiplied with the ZBB of f. So let us say it has some frequency dependent behavior. Okay, this is ZBB of f. Okay, so this gives you some VIF V1 of t, V1 of f. So again frequency dependent. Now This undergoes up conversion through the switching pair. To give you the output at a shaped output at plus or minus FLO or plus or minus FC, which is the carrier frequency. Is at the input node, correct. It's at the input node. So this is actually your VRF. So, and this Vin at the input node A. Okay. So now what has happened is the frequency response of ZVB of F has now been upconverted to a similar behavior to a slightly different behavior at the carrier frequency. So in other words, for example, if in this case ZVB of F has a low pass behavior, right? However, at your RF frequency you get a band pass behavior. Okay, and obviously this is a very powerful mechanism because you can use it, people have used it for very high Q filtering at RF frequencies. For example, we all know it is much easier to create a high Q filter at baseband, and it is much more difficult to create a high Q filter at RF. So if you actually had a node where you wanted to create a high Q filter at RF, you could use such a structure to actually get filtering at node A using an appropriate baseband impedance. So your RF voltage spectrum is shaped by ZVB of F and low pass becomes a band pass filter at RF. So the input impedance is clear that it is the same ZVB of F but translated in frequency at the input, to the input frequency or the LO frequency. Now, what is the advantage or disadvantage of this kind of current mode mixer compared to the voltage mode mixer? As it turns out, the noise and linearity of the current mode mixer are better than the voltage mode counterparts. Any idea why this could be? Now, one of the reasons is because you are driving it with an ideal current source. Okay? The switching mixer, the switches are actually in series with the current source. What do you know about anything which is in series with the current source? It tends to affect it much less than a voltage mode case. Correct? So, because of that, it is usually better. The noise and linearity are better than a voltage mode mixer. Now, obviously there are other reasons also. Normally, if you are trying to create these current mode mixers, you can make the linearity even better. For example, we gave the example of the transconductance transimpedance amplifier yesterday, where you make sure that the voltage swings at both the input and the output are very small, right? And if you do that, if you make sure that the voltage swing at the input and output are very small, you can make it even more linear. Because whenever the voltage is swinging, There will be nonlinear effects such as the switch, varying switch resistance, okay, varying CGS of the transistor. You will have all of these effects if you have large swings. By minimizing swings, you can make it even more linear in the current mode case. Okay, so let us look at some other characteristics of the passive mixer. So what kind of LO swing do you need in both cases? You would like it to be as large as possible so that you have a very low switch resistance, right? Okay, so let us say 0 to power supply and back. Is this a problem? Usually not a big deal, right? Many of these LC oscillators actually give you very large output swings. If necessary, you can buffer it up to very large swings. So it is not a huge problem except at high frequencies. Let us say if you go beyond 5 or 10 gigahertz, getting a large swing means you have to burn really a lot of power. Okay, so it's not a problem at moderate frequencies. And obviously it gets better, it gets easier to do this as technology scales, okay, because the parasitic capacitance keeps reducing. Okay, now the problem is, we may say, the swing is as large as possible, but does it have to be 50% duty cycle? We have said that so far we have assumed that the LO has a 50% duty cycle. Is this really necessary? Or let us go back and see, did we make any assumption as to the duty cycle, or did the duty cycle affect the behavior of the mixer in any way? So what really changes if we change the duty cycle of the LO waveform? Let us say the duty cycle of the square waveform was D. If you actually calculate the fundamental of the IF current in either case, okay, this happens to be 2 by pi sin pi d by 2d. This is the expression for the IF component we are interested in. So it depends on the duty cycle in this manner. Okay? Depends on the duty cycle in this manner. It has a sin pi d by d kind of behavior. Sin pi d by pi d kind of behavior. Okay? So now, this is the fundamental we are interested in. This is the conversion gain. Okay? Now you need to figure out at what value this becomes largest. Exactly. So in reality, if you want to maximize it, you would like to have an impulse sampling. So 0 duty cycle does not mean it's just 0. You are sampling it with an impulse. Okay. This will actually give you the best case. So that means that if you actually get a very narrow set of pulses, that will give you a very large conversion gain. So do you see any problems with this? Obviously generating those narrow pulses becomes a big problem. Okay, so obviously generating impulses becomes difficult. Precise impulses becomes difficult when you are working with these multi-gigahertz frequencies. So what people have done is they have arrived at some kind of compromise between what is easily generatable and what gives you more gain. So as it turns out, 25% duty cycle is very easy to generate. Okay, 25% duty cycle is easy to generate because if you actually use a divide by 2 circuit, we know that it gives you in phase and quarter share components. So if you have a differential divide by 2 circuit, it very easily gives you 0, 90, 180 and 270 phases. Okay, and by an appropriate manipulation of these phases, you can actually create these 25% duty cycle waveforms, and as it turns out, it does give you more gain. It does give you 3 dB more gain compared to the 50% duty cycle. So you get a 2√2 by pi kind of conversion gain when for D equal to 0.25. So this also has another advantage. The 25% duty cycle has another advantage, which is with 25% duty cycle, you will find that the LO waveforms are non-overlapping. You have 25% duty cycle waveforms. So you will find that the 0 and 180 and the 90 and 270 will never overlap. So which means that those switches are not on simultaneously, which means that the noise should ideally be lower and the nonlinearity is also lower. You can get both better noise and better nonlinearity.